down to 75. Okay, roll 'em. Rolling, rolling. Okay. Alrighty. Okay, so as I said I was going to do was take the names off the first homework as the list of interested parties. So you don't have to say here. This is the list right now that I'm putting into the registrar for people in the class. It was only 75 turned in the first homework, so there's no problem. So if you turn your first homework in, you should be okay. I'll just read the names. Bagger Afshar, Louis Alarcon, Maung Ong, A-U-N-G, Tamer Bakasev, Annapuma Bawander, Joshua Chang, Henry Chen, Phil Chang, Richard Chang, Sanchi Chow, Yu Jack Chu, Patrick Rossini, Lloyd Lin, Farzad Escafi, Sagnik Ghosh, Greg Gibling, Philip Godoy, Sean Gupta, Happy Sin, Albert Wang, Wayne Wang, Eugene Wang, Robert James, Cindy Kwan, Silu Chow Lai, On Lam, Daniel Lau, Michael Lee, Michael S. Lee, Matthew Leslie, Jason Lee, Shiji Lee, Jarrett Yelang, Joyce Liang, Michael Liao, David Lin, S. Lin, David T. Lin, Kevin Lin, Michael Lin, Ben H. Lin, Ben H. Liu, Nura Cham Liu, Philip Liu, Sandy Liu, Vincent Liu, Long Da Liu, Chao Chi Lo, Victoria Locke, Quan Cheng Liu, David Mason, Sidhar Mishra, Kurt Moen, Ben Nu, Fang Nin, Jen Yu, Archie Pelagos, Taming Chi, Carl Shuka, Anatoly Smolkin, Grace So, Venkatram Subramaniam, I think. Jude Sun, Lee Sun, Eric Swanson, William Sang, Whelan Toon, Jonathan Yoklum, Sanhan Vantaka, Michael Vo, Stephen Volkman, Beverly Wang, Frank Wang, Johnny Wong, Ying Wu, Guanan Zhu, and Yong Yang. Okay, so if you're not on that list and you think you turned in the first homework, or you want to be in the class, actually, because we have 5 spots left, come see me at the break, okay? I don't want to do it now. Okay, any other questions? Any questions? Let me tell you what's happening next week. It snuck up on me faster. I have a few trips this semester that I'm going to have to do. One of those trips is next week. I'm visiting MathWorks in Boston. And what I'm going to do is do the first half of the lecture on Monday, and then I'll get someone else to teach the second half and the Wednesday lecture. So it'll be the same as the notes. It'll just be my stuff, but unfortunately I won't be here. Sorry about that. And there'll be a couple other times. I got a couple other trips that I'm going to have to do. And I'll try to get good substitutes for you, but that's next week. Any questions? Any questions about material I've been over? Or? Okay, let's roll. Okay, so what we're going to do is finish up the single transistor work. We're going to jump up to 2 transistors. Boy, we're really going big time here, right? So we'll have 2 transistor circuits. We'll talk about those a little bit, and then we'll go into current sources, and hopefully I'll get over to current sources today. Okay, source follower. We talked about that at the beginning, or at the end of last lecture. Okay, this is this circuit right here, very common for buffering. As we talked about at the very end of last lecture, we kind of calculated the gain was like 1. The input resistance, looking into this circuit, looking in here, is going into the gate, right? So that's infinite Okay, so again, this is a nice circuit to connect to the output of something else, right? I mean, if you, like we talked about that common gate circuit, which had that source on the input, which was a really low resistance, that's not a good circuit to hang on the output of something else, right? Because it kills the output resistance, right? These kind of circuits are really good because it's infinite, right? Doesn't cause any loading at all, at least resistively. Unfortunately, it's not totally clean after the midterm when we start doing frequency response. Of course, this is a capacitor here. This gate is a capacitance. So it actually does provide some loading. It's capacitive loading, which slows down the circuit. But it's not like a resistive loading problem, which you're worried about now. Okay. High input resistance. Output resistance is low, right? Because it's looking up into this source, which is in parallel with RS. So looking up into the source, we talked about last time, that's roughly like 1 over GM. Okay, or it's 1 over GM plus 1 plus chi if you haven't grounded off the substrate. So that's pretty low, tens of hundreds of ohms. So that's actually good, right? Because if you want to drive another stage, you want to drive from a low impedance. So an ideal buffer has infinite input resistance and 0 output resistance. So source followers are not perfect, but they're good, right? They have infinite input resistance and low output resistance, not 0, of course. Okay. How do you make it lower output resistance? You can make this RS smaller, right? The smaller you make that, the lower the resistance is here. Also, smaller RS means more current. More current means lower GM. So to make this thing really a good buffer, you just keep pumping more current through it. Make this have smaller value output resistance. It's pretty straightforward. Okay, the DC design, DC analysis of this. I think I did that here, right? So let me just do it. Okay, so let's say I want to have, this is RS, and I'm doing the DC analysis, or the large signal analysis, okay? Here's V in, here's V out. Capital letters means large signal. If I want to have, if this is at VDD, and let's say again, like usual, I want to sort of bias this in the center of the range. So let's say my design problem is, or design specification is to have this set out to VDD over 2, okay? Then what's the current that's going to be going through this transistor? Well, that's pretty easy, just like the common source stage, right? I mean, the current here is the same as the current here, so IDS is simply going to be VDD over 2 divided by RS, right? So that's pretty easy to figure out what IDS is, okay? Once we have IDS, right, so now we've got what IDS is, then we can calculate VDSat, right? VDSat is equal to 2 IDS K prime W over L to the 1/2, right? So once we have IDS, we can calculate VDSat. Once we have VDSat, okay, so now let's say the question is, what is the input, what is the DC voltage we need at V in to get out to have this thing biased correctly so the output is at VDD over 2? Can someone tell me what the answer to that is? We can I should also maybe calculate VT. It's going to be equal to VT0. Let's say this is, as it's shown here, it's not connected to the source, right? So it's connected to ground, so we have some body effect. So it's going to be VT0 plus, gamma times 2 phi b plus VBS to the 1/2 minus 2 phi b to the 1/2. Okay. Okay, so we have to calculate this, but we know what VBS is, right? Because we know what the voltage at the source is. This is at VDD over 2. So VBS is minus VDD over 2, so we can figure out what VT is. So we have VT and we have VDSat. So tell me, what's the DC voltage at V in that we need to have to get the output equal to VDD over 2? I know you all know this. There is not one person in here that doesn't know this answer. I know that, right? So it's just a... Okay, let's go for it. Great. All right, Vn equals VDSat plus VT plus plus 1/2 what? 1/2 VT? 1/2 VT. Yeah, VDD over 2. All right. Why is that? I mean, this, what you gave me here, is exactly right. It's equal to VGS, right? So that's voltage from here to here, right? But we have to add on the voltage down to ground here, so that's the VDD over 2. But, you know, in terms of, I told you a couple important things last time, right? Looking into the source, it's 1 over GM. Looking into the top, you know, with a source degeneration, look into the drain, you get this GM times RS times R0 is the output resistance. Here's another really important on that order, if not even more important. And we've talked about this, but let me just begin to get the way to this is how we'll do DC analysis throughout the whole year, in effect, right? And we're beginning to do it now to a certain extent. The way we generally will do problems is we will, the way I'm going to show you how to do this will seem kind of, okay, that seems reasonable. At some point in time in the term you'll say, why does he say that? It just doesn't make sense. This is not true, right? So it's really a fairly sophisticated thing I'm going to show you right now. And it's going to be really important in doing DC analysis as we go on. So here's the point of view we take. We say we know what IDS is. Quite often what we will do is set the current. Now this is being set by the specification of the output voltage. Other times we'll set it by current sources. So quite often the way we will do circuits is set currents by current sources. Okay? So the controlling variable in some sense is the current. Right? What you can easily get into, or what probably what you've sort of thought about these kind of circuits in the past, is the controlling variable is voltage. I mean, like here, I sort of did it. I said, okay, let's figure out what the Vin is in order to figure out to support a certain IDS. In actual fact, in the future, what we'll begin to do is to reverse that. We'll say, okay, given IDS, here is what Vin has to be. And this will be very important when we have multiple stages of stuff. We will work out exactly what the input Vin is by figuring out what it has to be in order to establish what the current is. Okay, now what do I mean by that? In other words, if I tell you the current through this device is IDS, and let's say that's established, then what you can tell me is what the voltage is at Vin. You see that? That's what I'm saying here now. And why can you tell me that? Because if this device, now I have to tell you one more piece of data. I can tell you the current's IDS. What other thing do I have to tell you before you can tell me what the voltage is at Vn? What? Mode of operation, exactly right. You have to know the region of operation. So here's how you think about this. You assume that it's going to be in saturation. Okay? If it's not in saturation, you're fouled up. Okay? You're going to have to fix that later on. You're going to have to do some checks to make sure that's true. But assuming that you're in saturation, then you know what Vn has to be. So if I tell you this IDS is 10 microamps, you can tell me that Vn has to be 1.2 volts because you will go and do this little calculation right here. Okay, you will know what this has to be. You will go here and you'll say, this voltage here is a VDD over 2, and this voltage will have to be a VT plus a VD sat above this voltage. And you'll be able to calculate Vn is. Now why that's weird is this, right? Look, that's a gate, right? Gates float, right? And why it's going to seem strange when you really kind of think about this is, how can you tell what that voltage on the gate is when it's floating like that, right? But see, it's kind of I want to call it recursive, or I mean, not recursive is not the right word, but what we will do in very complex circuits, we will go through and be able to figure out what the voltage is on the gate, right? Because that's the only voltage it can be to support the current that we assume is going through it, right? Okay, so you get this? So it's a little bit of a, so I'll keep coming back to this, but here's the first shot at it. So I mean, if I tell you IDS is something, you can calculate what Vn is. And if you have a more, I'll just show you why this is useful. If you have a more complicated circuit, let's take this circuit. let's put a current source here for a second, okay? Okay, so here is a very typical arrangement. This is a current source up here. We'll start to use current sources as loads, so just assume it's an ideal current source, and we'll realize this is basically a single transistor, not too distant future. By the end of this lecture, hopefully. Okay, so tell me what the voltage is right here. That's the question I may want to ask. And people have already asked me, said, you know, geez, and I'll tell you all the IDSs are equal to 10 micro. This current source here is 10 microamps. So let me, yeah, okay, so this is 10 microamps or something like that. And let's assume this voltage here sets this equal to 10 microamps. Okay. So I may ask, what's the voltage at this point right here? You say, and someone, like I said, somebody's already asked me, well, how do I calculate what VDSs are? Right? We know how to do this VGS business, but how do we know what a VDS is? You can't tell a VDS, right? It's like looking at a current. This is a transistor, sort of like a current source, right? It's kind of a non-ideal current source, dependent current source. And you don't know the voltage across the current source. Other things set the voltage across the current source, right? I mean, how do you figure out the voltage across? You have to look and see what it's connected to. If it's connected to a battery of 1.2 volts, then you know the voltage across the current source. It's set by this other element which has something controlling it. Okay. Now, here's where we get to this. So let's figure out what this one is. So I can't tell what VDS is by looking at this transistor. I got to look and see what it's connected to. Well, I look and see that it's connected to this resistor up here. I mean, this current source up here. Well, that doesn't help. You know, current sources don't set voltages, right? So I keep looking around. I look over here. And I've told you that this is 10 microamps. So I can figure out the voltage that has to be on this gate. If this is at VDD over 2, we know that this voltage right here has to be VDD over 2 plus VDSat, thank you, right? Plus VT, right? So we know the voltage there. Okay? If we know the voltage there, we know the voltage across this VDS. We can then check to see if this device is in saturation, right? And we can do all sorts of other things. Now, what's really weird about that? Let me just finish up here and then I'll take a question. What's really weird about that, I'm acting as if this gate is setting the voltage, right? But this is a floating gate. This is infinite resistance. That's what's so weird about this. But here's what has to be true. This is the only voltage this can be to support this current, right? So what you're going to have to do in your circuit design is, basically what you're going to have to do is you'll have to set this voltage and do some other things to make sure that this voltage is correct in order to support this current that I have required. So in the end of the design, this voltage is going to have to be at this value. So the way we do this stuff is we assume it's true early on, and then just keep working through to figure out how to make it that way, right? You get that? So it's fairly subtle. What's weird about it is that we're going to use this voltage here like it's a controlling voltage, like it really sets things. And that's how we'll deal with it. But the only reason it's going to work out like that is because when we finish up, we'll be consistent with our specifications on how much current's going through here and so on. In fact, what's the voltage right here? We can calculate what this voltage has to be. What's it going to be? It's going to be VT plus the VDSat. VT0, right, because this is grounded, right? So VT0 plus VDSat of this transistor. That'll have to be the voltage here to support 10 microamps. Okay? Question over there? Yeah, sorry. Yep, got it? Okay. Okay. This is pretty important. This little thing right here. Let's get this idea that we can, once we know the currents, we can treat this like a something that allows us. It's like a voltage source. We'll kind of think of this like a little voltage source of size VT plus VDSat. A little battery. That's how we'll think of it. Okay. It's clearly not a battery, but that's how we will use it when we do our design, our analysis. Okay. you can easily, this is the easy problem, given V out, figure out V in. Given V in, figuring out V out ends out more complicated. It ends up with a quadratic, right? So that's just life. So just don't be surprised when you find this quadratic. Here's a pretty simple problem, but it ends up with a quadratic answer if you have to go that way instead of going backwards. Quite often, fortunately for design, we're going backwards. We want to set the V out to some value, so we need the V in that sets the V out. So generally, that's the normal problem you solve. Typical analysis problems are the other way, right? Typical classroom stuff, right? But that's not. But you can solve quadratics, right? After this homework, you know how to do that. Okay, let's quickly redo the small signal stuff because we've already done this problem already in effect. What's the output resistance of this circuit? Okay, output resistance, looking into here, is going to be RS in parallel with looking up into this lead. Looking up into there is the same problem we solved last time, right? Well, we ground the inputs at the independent variable and this gate to 0. VDD, this is small signal, so VDD is like a small signal ground. So we're looking up into the source, something with the gate grounded and the drain grounded, and that was exactly the case of the common gate circuit. Remember? That was the input resistance of the common gate. Common gate looked like this, right? Here's the... so looking into here, this is Vn. If we're looking into this thing, and if this output resistance is small, remember if we have RD, so it's the input resistance of a common gate when the output resistance, the drain resistance, is very small. Okay, so we solve that problem. And how do we solve it? We solved it like that. If you remember, well, you can look back at this. If we're calculating output resistance here, we're looking into this node here, and effectively, I don't want to solve the parallel resistor problem again, so I can basically look, here's the output, right? So it's, as I've shown here, it's a parallel combination of RS looking down and looking up into this circuit right here. So how do I do that? I put a test. So let me just, I don't want to redraw this. So looking up in this direction, let's put a test voltage, V test, and calculate the current that goes in, and we can find the resistance. If I put a test voltage right here, that defines the voltage on this side of this current source, right? This is grounded, so this defines VGS, right? VGS equals minus V test. So now these current sources, this current source right here, is equal to minus GM times V test. I can change the polarity and I can change the direction of the current source. GMB times VS, well, VS is simply equal to V test, right? So I can change the sign of this and change its polarity. So what do I have? I have current sources which are dependent on the voltage across them. And I have R0, which is a resistor. So what are those? Those are resistors, right? So I end up with this circuit right here. 1 over GM in parallel with 1 over GMB in parallel with R0. So the output resistance looking up into here will be, you know, including RS. It's RS in parallel with all of these things. So here's the output resistance. Okay. And last time we very quickly did the big GM, but let's just do it again here. That's pretty easy. Here's Vn, big, here's RS. Big GM, what do? We ground the output and we calculate the current going into this. Okay. What's the current going into this node? Well, what it's going to be, if this is grounded, okay, so we're going to basically get GM times VGS, right? And VGS is simply equal to GM times Vn. So big GM is equal to GM. So gain is GM times this. Okay, I've solved it exactly here. Okay, just without doing the big GM stuff. You know, it's a few lines. It's not too difficult. But so this is the answer, right? So this is V out equals, so here's the gain. So gain is equal to GM times RS over 1 plus chi times GM RS. So let's look at some limits of this.
Question.
Yes.
Does the current direction matter here?
Does the current direction matter
The
here?
dependent current source.
It flows out, right? So what are you worried about? The gain or the sign of the sign of the current source? These current sources? So he's worried about the sign of these current sources, the fact that I flipped them around and stuff. What I wanted to do was to get to this, right? And the way that's true is only if I have a current source. This is V, well, it's V test in this case. This side is grounded, right? And this current through here is GM times V test, right? If that's true, I can replace that as a resistor because the current goes in that direction if you apply a positive voltage here, right? Right. So I have to have the right polarity and everything. If this current was actually going in this direction, I applied VT here, that wouldn't be a resistor. That'd be a negative resistor, right? Which is the thing with gain, actually, right? Right? Make sense? Okay. All right. So I mean, it's got to. The only way you can do this replacement here is it's got to be just like this. You put a positive voltage here, current flows that way. So we got to have a current source with the same polarity. So polarities are important. Right? I often will, and maybe it's a little confusing to you. Sometimes I haven't done it yet, but I will do it. Okay. I won't care. When we have a bunch of stages together, I won't care too much about the gain of the whole thing. Okay. Typically, I'll tell you why. Just a little foreshadowing what we're going to do today, actually. We'll quite often make circuits like this. They'll have differential input with a single-ended output. Okay, so this will be Vn plus and Vn minus. I don't really care too much about the polarity of all the stages inside here because in the end, all I have to do is just name these things differently, right? If I want to have positive on this terminal to this output, I'll label that positive. If I have an extra gain stage inside here that flipped the sign, all I'll do is just rename the inputs. And so often polarity, whether it's plus or minus gain, is not really very important, you know, typically because we work with circuits like this quite often. So, but it's important for doing replacements of resistors with current sources with resistors. You got to be sure you have the right direction there. I don't think we'll ever see a current source in the opposite direction, right? That's actually, like I say, a gain stage. Okay, let's look at the limits of this. AV equals GMRS over 1 plus chi GMRS. So this is the whole equation, body effect, not throwing anything out. And remember what let's look and see what we're talking about here. We're talking about, here is RS, here's V out, here's V in, here's V out. Okay. Now, what happens if we make RS very large? Okay. How might we do that? Let me show you one way you can do that. We can do this. We can put a current source down there. Okay. If I put a current source down there, and this will set, let's say make it 10 microamps, this will then set IDS through this transistor, right? So I've got a nice DC current set, right? I have, let's say, 10 microamps of current here, but that's infinite resistance. So the small signal resistance of a current source is infinite, right? Perfect, an ideal current source like this one. So what's that mean? That means RS goes to infinity in this equation. So what happens when RS goes to infinity in this equation? What does this go to? 0? So this term here gets very large compared to 1. And the GMRS's will then cancel out. So we end up with 1 over 1 plus chi. So as RS goes to infinity, this thing ends up with 1 over 1 plus chi. So it doesn't quite make it to 1 if you have not grounded, if you have not tied the substrate back to the source. If you tie the substrate back to the source, then this term is not there, right? It's not that chi goes to 0, but it's the VBS term. The GMB doesn't provide any current. So we end up with nearly 1. If we have an ideal current source, substrate tied back to the source, then you end up with a gain of 1. Okay, so that's pretty neat. And it's reduced from 1. It's typically 0.8, 0.9 if you have typical values of chi. Okay. So notice as you make RS larger, this thing approaches some sort of value, some asymptote, depending on whether you tie the substrate off. Is there anything else to say about that? I guess that's just about it. Voltage here is VT plus V. So remember this is the VT plus VD sat above the source. So here's out. You can easily figure out the DC voltage is here. The gain is nearly 1. The output resistance is 1 over, roughly, typically, it's like I talked about in the common gate stage. Looking into the source, it's like 1 over GM, or 1 over GM times 1 plus chi. Okay, any questions about that? Yes?
Sorry, the math suggests that you can't really cross out chi, but you said you crossed it out because there's no current contribution to...
yeah, then let's redo, if I redid this problem, okay? If I redo this problem, I would, well, let's go back. Let's go back here. Redo this problem if Vs is 0, right, because I've tied the substrate back to the source, right? This is VBS here, right? Or VSB, I guess. This is VSB. So if VSB equals 0, that means this current source is gone. If that current source is gone, this is gone. Okay? And it's this thing right here, this GMB term, which is going away. GMB goes away, that gets rid of this chi term right here, and that gets rid of the chi term there, right? So probably need to take it through once to see that, but if we tie off that substrate, this current source is out of there, and that chi goes away. Okay. Any other question? That was a little fast there. Okay, summary. These are, I told you, you need to memorize some equations, and this is a set of them, okay? So this stuff we've been doing the last week and a half, last lecture and a half, is common source, gain, GMR out. This is always true, right? So you don't have, that one should, this comes from definition of circuit transconductance, right? For this circuit, big GM is equal to minus little gm. Little gm is the device, that's transconductance, the transconductance of this transistor. R out is simply R0 in parallel with RD. You should begin to look at a transistor and just sort of think about this little R0 connected between the source and drain. So you look there, you see RD this way and little R0 this way. You got to worry about the fact that there's a dependent current source inside there. But if we think, well, this is grounded and this is grounded, we see that that dependent current source has no current going through it. So it's simply RD in parallel with R0. So it should be able to just use that kind of set of mnemonic devices to figure it out. If I go in and plug in for R0, I guess I did that somewhere in the notes here. You can calculate, if we let RD be much, much greater than R0, okay, in other words, this is much, much larger than this, which is difficult to do, I told you, until we make this a current source. Then you end up with this as sort of being the limiting value, the maximum voltage, maximum gain you can get. 2 over VD sat divided times 1 over lambda. So 1 over lambda we can affect by making the channel length longer. Remember that? Okay, so we'll give you the parameters on how you can do that. That's a device change, and well, it's not a device change, but we're using the fact that a longer channel length changes lambda. That's pretty expensive. It's actually bad also from a frequency response standpoint. If we make, remember I told you that the input gate of a transistor looks like a capacitor, right? That's what it is, right? the size of that capacitor is W times L times some oxide capacitance per unit area. So if we make, generally we set W over L's. If we make L longer by some factor, let's say it's longer by a factor of alpha. So if longer by a factor of alpha, the ratio is unchanged because we'll make the width longer by a factor of alpha. But the area, this is the area of or the capacitance of the transistor, gate capacitance, is going to go up by alpha squared, right? Because alpha times W times alpha times L will give an alpha squared increase. So if we make the L 2 times minimum size, the area of the transistor will be 4 times minimum size. That's 4 times the capacitance. Capacitance slows circuits down. So you don't want to do this business of changing lambda unless you really have to by just increasing the length, because it really adds capacitance, okay, which slows down the circuit, which requires then more current probably to drive that capacitance, which requires more power. So you got a slower circuit that requires more power. That's not good, right? So this is kind of a, but sometimes you need to do it, and sometimes it's the best solution, right? So don't throw it out. But the other way to to improve things is to make VD-SAT small. How do we make VD-SAT small? VD-SAT is 2 IDS, okay, over K prime W over L all to the 1/2. So how do we make it small? We have low current. Low current also slows down the circuit, so that's also a little bit of a problem. Make the transistor bigger, W over L bigger. So so as a designer, these are your parameters. You can play with IDS. You can play with W over L. K prime's pretty much given, except for NMOS and PMOS, right? PMOS K primes are typically 3 times smaller than an NMOS K prime, right? K prime of NMOS is about 3 times the K prime of a PMOS transistor. So what do we want down here if we want more gain? We want this to be large as possible. We want K prime to be large as possible. So that argues for making it N-channel transistor. So if you want more gain, you probably want to have this N-channel transistor to get the K prime high, make the transistor big, and reduce the current. And also play around with length if you want to. Okay. What other things we can do? Well, we can put a degeneration resistor here. That changes big G sub m to equal to this. Degenerates the transconductance. Instead of being little g sub m, it's equal to this factor right here. The output resistance is equal to this whole thing right here. R0 times 1 plus gm times 1 plus chi times rs in parallel with rd. So this is the looking down. This is that formula that's so important, this part right here. Typically the one's not important, so it's typically this. Okay? And you multiply GM times R out and you get AV, right? Any questions about that? So that's really important, okay? On your midterms, you'll have a sheet of paper you'll be able to bring in, okay? You can write as much as you want on one sheet of paper. You can put all the formulas you have on it. You might just get these important formulas down on your little sheet of paper and just kind of get used to using it, because you're going to use these formulas over and over again, okay? So. Know it there. Pardon?
Is it two-sided?
A 2-sided sheet of paper, yes. No one-sided sheets. Okay, well then, no. You can write as much as you can on one sheet of paper. Okay. Right. Okay, source follower, the buffer, gain of 1. Just talked about that. Total gain's this, R out equals this, AV max is this, it goes to 1 plus chi if RS is much, much greater than 1 over GM. Common gate. This is also a pretty good gain stage, a bad buffer, right? Because it has a low input resistance. It approximately goes as 1 over GM quite often because you're looking into the source. But pretty good gain, same gain as the common source stage. There it is, common gate, common drain, and common source with degeneration is kind of the basic element. So these are our basic building blocks, okay, for gain and active circuits. I mean, we'll what we're going to do, and plus the circuit I'm going to show you right now, which is really kind of as you will see, pretty much the same circuit as we have here. These are the basic units that you will use to put together and make op amps, make everything else. Any question about that? Okay. Here we go. Big step. 2 transistors. All right. Look at this. Okay, here we go. So 2. Here they are. So major complication. Okay. So in actual fact, this we'll actually put some transistors up here and put a transistor down here. But it's really 2 transistors are really driving this circuit, right? This will probably be the most complicated circuit we'll work with as a unit. We'll make up transistor circuits, op amps and stuff, they'll have 20 transistors in it, but they'll never get to be a more complicated unit than this one. We'll break it up into blocks. Okay, yeah. Here's your mic. I will stop in 5 minutes. Yeah, I was watching. Give me. I get my time here. Right, sorry. Okay, so this is our new circuit. Now, how is it different? It's like I showed you a second ago, right? It's basically we're going to have 2 inputs and a V output. So this is V in plus, V in minus, and V out. V in plus, V in minus, and V out, actually for this circuit, is going to be a differential output, so I should draw it like this, actually. This has got a V out plus and a V out minus. That's actually what this one is. So here's V in plus, let's call this V out plus, V in minus, V out minus. So it's 2 inputs and 2 outputs. It's a fully differential circuit. Okay? Turns out quite often, typically most circuits, like op amps and stuff, will start off with this as the first stage. Okay? We'll end up after one stage or two going into the single, like a common source or common drain that we just showed you there, because it's less transistors. I mean, there is a few more transistors here, so you don't want to use any more than you have to. But quite often you come in with a differential input, so that's actually fairly typical. Okay. Now, how do we analyze this? We could analyze this with these 4 variables: V in plus, V in minus, V out plus, and V out minus. Turns out that's not the convenient set of 4 variables to work with. So we're going to do a variable transformation. And it's only, this variable transformation only makes sense because of just the common ways we use this circuit and the common way we design it. So this is nothing sophisticated. It's just we're going to define linear combinations of these 4 voltages, or linear combinations of these 2 inputs, linear combinations of these 2 outputs, to define 2 new variables that are exactly equivalent. Now let me just finish up a little bit more time with this circuit. So I will do that in this next step. If you look at this a little bit, you sort of see this looks like a common, if this happened to be a ground, this would look like a common source. If you look at this, it looks like another common source. So this is kind of like 2 common sources connected together, and we call this the tail. And this tail is the tail current source that goes to some supply down here. Okay? And this actually can be a resistor as well as a current source. Okay, so we can have a current source down here, we can have a resistor down here, and the circuit still works the same. Parameters a little bit different. We have 2 loads up here. These are the load devices. Okay, so 2 driver devices, 2 load devices. These are resistors here. We'll turn these into current resistors, into transistors pretty soon. And there's a current source on the bottom here. So how does this circuit work? So let's in the next 2 minutes I got left, right? Let me talk a little about the DC part of this thing. Well, let's define the new variables first. I just want to do that. New variable 1, and this is for DC and large signal and small signal both. We will define something we'll call VN differential. VN differential is simply Vn plus minus Vn minus. It's the difference between these 2 voltages. Okay. Similarly, V out differential is equal to V out plus minus V out minus, or V out 1. I guess I use 1 here and 2 there. Totally equivalent, right? V out 1 minus V out 2, right, or whatever. So just basically, differential is the difference between these 2. This is differential. The other, that name you're kind of familiar with. Another name you may not be familiar with, we call common mode, okay? All common mode means is the average value equals average value, okay? Definition. So what's the average value of the two inputs? Average value of the two inputs is V in common, okay, is equal to V in plus V in minus divided by 2. V out common is equal to V out plus V out minus divided by 2. Or V in 1, V in 2, V out 1, V out 2. Okay? So these are the two variables, differential and common mode. And you can invert these expressions, right? So that V out 1, let's go use 1 and 2, I guess, is equal to V out common, which is the average value, plus V out differential over 2. And V out 2 is equal to V out common minus V out differential over 2. That's just taking these equations and inverting them. So you can go back and forth. Just linear combinations. Does this work? If we average these two voltages together and divide by 2, what do you get? Add these together, we get 2V out common. Divide by 2, we get V out common. So sure enough, this average value of these is V out common. If we take the difference between these two, this minus this, V out commons cancel. V out D, VOD over 2 minus a minus VOD over 2 gives you VOD. So sure enough, the difference between these is VOD. So that works. Okay. Little break. 5 minutes. Okay. Still homework ones? Okay. Okay, thanks. Yes.
Question. I didn't realize that I have to put the net listing. Actually, I thought I only needed the graph. So can I turn it in?
Again?
Right now?
Do you have the net list?
Yeah, I do have it. I have to print it out though.
Print it out and, yeah, if you do that, sure.
Okay, so I put it in your box in your office.
Right.
Okay, thanks.
Professor, did you have to, can I check my names on your moving sheet? Last name XU.
SU?
X.
Guanon?
Yeah, why not? Thank you.
I think I not on the list, but I turned my I turned it into the box and Corey.
Oh, did you?
Yeah, after.
Oh.
I think it's a little late though.
Ah, okay, so what is your name?
Jason. SRISATHAP. So, do you know what happened to my homework?
It's probably still in the box. Yeah, they'll probably get it this time. So, yeah, okay, so. Okay.
Two things. Hi.
Hi.
Two things. One, he marked it wrong, but then he crossed it out and he said it was correct, but he still added it in.
Okay.
So 94.
Why don't you put a little note on this one like that and just turn in with this in?
Oh, okay. And one more thing was on this past homework, he said that, so I'm asking about the operating conditions, right? So for saturation, all I did was I took the inequality of VD sat has to be greater than to VGS or VGS1 minus VT, and then I took VDS2 has to be greater than equal to VGS minus VT. I just added up the inequalities. I added up the inequalities and I got VDS, which was VDS1 and VDS2, is greater than VGS minus 2 VT.
Yeah, okay. You got to watch it there. I mean, the first VDS has the second VDS is part.
I just asked,
make sure.
That was the one I asked you on it.
Yeah.
It was like 2 VT, right? But then I was thinking about it. It's like, why wouldn't it be just a single VT?
I'm not sure actually. I don't know what.
So, I mean, I'll just.
It's,
They can go first.
okay.
In the first problem, you said that this voltage is totally determined by this current source, okay?
Yeah.
And this voltage is due to from determined by this current.
Right.
So they are definitely independent from each other.
Yeah, but if
So, as well as we are in saturation region, for example. And so I just want to know, you said that we can put a DC voltage source here to fix that or the current voltage. The voltage which comes from this system.
but this voltage, if you put something there other than that voltage that we talked about,
There comes some sort of problem, okay? So I mean that do we have to put some DC voltage source to fix? So we don't have to. So where's the problem? So if we design the circuits, how can we put another voltage, DC voltage here to make the problem, to cause the problem? You know, this voltage comes from the
definition. So you gotta think it's a design problem, right? So I'm saying, okay, V out has to be this.
Yeah.
Okay, now, if V out has to be this voltage has to be,
Yeah. And how can we get this voltage?
well, that's going to be part of the design problem. But, so you'll know what that voltage now has to be,
I know what's happening.
and you're going to have to do something here. That's but the only control you have is right here, right? So this voltage is going to have to be something that will set this voltage right.
Does this voltage have any effect on this voltage?
Yeah,
Because it just determines the current.
yeah, but a small change in this voltage makes a huge change here, right?
Oh. Yeah, of course.
So you'll have to figure out how to make this voltage right to make that voltage right, which will make that voltage right.
Because it has a very indefinite resistance and it's very little over GM.
Yeah, you're at the gain of this whole stage here, right? Yeah, right,
Very
yeah.
hard.
So millivolt change here will change as volts.
Both.
So you see a problem with this circuit,
Yeah.
right? You've been,
Maybe it goes from its linear region to
yeah.
some biasing point to a very high.
Easily, what can happen is it'll move out of, it'll get out of saturation. That's what'll happen if you don't do the right thing, right? Sure.
Because, like, number one, I think I got marked, well, I got different answer because I used different curves.
What you do, if you got any complaints about the homework, make a little note and make sure, put big letters, homework 1, please regrade, and put your little story down, and we'll just give it back to them, okay?
Okay, so do I put like another sheet of paper in front of it?
However you want to do it. Just make sure it doesn't get lost, it doesn't get disconnected, yeah, right?
I mean, like,
I better go. After class? Want to do it after class?
okay, so
Yeah.
should I just hold on to it until after class? Or instead of trying to find it again?
Well, why don't you put what you think is the right answer?
Well, I mean, I had minuses, but then I was thinking, and then you said,
Well, don't listen to me. You put what you think is the right answer.
don't listen to you.
Don't listen to me. Ignore me. I haven't done that problem yet. You've been working on it. You should know better than me, right?
So I haven't turned in homework 1, but I wanted to.
Okay, your name is?
Two fan PHU. You fan PHAN.
Turn it in. Okay. Okay.
Who's the reader for this?
What?
Who's the reader for this class?
Who's the reader for this class? I forget his name, right? Well, I'll give you his. I'll have him put his email on the thing.
Because if you have questions about
If you have questions on your homework, make a little sheet of paper, clearly label homework 1, okay, and write down say, please regrade, and here's why, okay, and turn it in again with this right here, and we'll give it back to him, okay? So that's the strategy for any grousing about the homework. Okay. Okay. Got that? Okay. Let's move on. Okay, so differential pair. So let's talk a little bit about how this circuit operates in the DC large signal. If you go through some fairly nasty math, if I can find some fairly, where's my, oh, there it is. If you go through some fairly nasty math, write the equations for this whole thing, okay? It's not real nasty, but I mean, here is what happens as a function, as we change VID. Okay? This is the differential. Now we're talking about DC right now. So this is DC analysis on large signal. Okay? Okay? For large signal, if we take, and what I'm doing, what that means is I'm taking these two voltages and I'm changing them. This one going up, this going down. So that's what I'm doing. I'm leaving the average value constant. Okay? All right? So that's what I'm doing. Okay, if we have, and I'm looking at the differential output voltage. I'm looking at the difference between these two as well. Okay? So I'm not very sensitive to the average value then, because notice there's symmetry about this circuit. This side of the circuit is exactly the same as this side. So if the voltage on this side is the same as this voltage on the input, and this transistor is the same as this transistor, and this resistor is the same as this resistor, what about this output voltage? How is it related to this output voltage? It's going to be the same, right? It can't be. There's full symmetry here, so there's no reason for that to be anything different. Okay. All right. So these voltages will be the same for a common mode. Okay. If we make a differential change here, that breaks that symmetry, and that means this output then will also change. Okay. And so we'll see a differential output. So that's the case I'm looking at right now. So I'm looking at the differential output voltage as a function of the differential input voltage, large signal. What happens is, as I change these, as I increase this voltage up and decrease this one, now something here, and this is going to be really important, this is a point of middle of, so if you sort of think this being have symmetry here, this is sort of halfway between these two positions, right? So if I sort of, there's no linear ramp going on here, but just sort of conceptually think about, this is VI plus, right? And this is VI minus, right? So you sort of think VI plus here, VI minus here. Here's a point halfway between these two. Yeah, it's a transistor, a bunch of stuff's going on there. But what might you think the voltage at this point will be? Sort of by symmetry considerations, right? This goes up and this goes down, everything's sort of symmetrical. You might think that center point turns out to be 0, right? And I'll make some better arguments for why that's true, but it really is. As we increase this decreases by the same amount. A way to think about it is this current in this side will increase, okay? As we decrease this side, we're decreasing VGS, the current on this side is going to go down. Since everything's symmetrical, this delta I up is equal to this delta I down. If I have a resistor down here in this tail, what's the current through that resistor? Because that'll tell us how much voltage change happens in that node. 0, right? If this current goes up and this current goes down by an equal amount, this current goes in and this current goes out in some sense, there's no net current down here. Delta ISS equals 0. At least that's the current through this resistor here, right? There's no change. This current source, of course, never changes, right? So that means there's no voltage change here. So that's important. We call circuits or situations like that a virtual ground. It's virtual in the sense that it's not really connected to ground, but it acts like it because of the way the circuit works. So it's a virtual ground, okay? But once you can make that assumption, it simplifies lots of stuff. Yeah.
Like, is this, so this is assuming that both transistors have, like, all the same parameters and things like that, or no?
Yes.
Okay.
It assumes everything's exactly symmetrical on both sides.
And when in general can you assume that? Like, usually, or is that typically the case, or?
For this circuit here, or in general, I mean, elsewhere?
I guess elsewhere, or, yeah.
We will see more virtual grounds, okay, but they don't pop up everywhere, right? They're really nice, right? I mean, if you can call a node a ground, wow, that's just great, right? I mean, no more calculation, oh, we're home free, okay, right? So you would like to identify them if at all possible, right? But they don't show up too often. This is probably one of the most important places where it shows up. I'll show you the other place where it's important. It's almost more an application. And that is, and you've probably seen this before, right? If you take an op amp, this is a full, high gain ideal op amp, which I'm sure you had in 105 or whatever, and we, connect it like this. There's all sorts of ways you can connect op amps, put feedback around them, right? But this point here, well, this is actually a bad case. Let me take a better one. So this is a typical use of an operational amplifier, right? You take feedback around it with a couple of resistors, and this defines a gain, right? V out is equal to minus R2 over R1 times V in, right? So that's a nice little circuit you often use. This node right there is a virtual ground. That's a virtual ground right there. Okay, so that's probably the other really important place. The input node on an operational amplifier is always a virtual ground. Right? Much more. That one happens because of the high gain of the feedback that causes it. Okay, virtual ground. We increase VID in this direction. So I'm having this lead go up and this one go down. This is staying at 0. What's going to happen to these transistors? What am I doing here? I'm decreasing VGS. So this transistor is cutting off, and this transistor is turning on. How much voltage change do I need to have before this transistor really begins to turn off, really cut off? So let's call this voltage 0, or to start with, okay? What is this tail current source is ISS, and that corresponds to some VDSAT, right? We can calculate what that VDSAT is. So let's call that VDSAT. Let's call it VDSAT. Okay, we know that value, right? What is the voltage on this gate? What does it have to be? If this is 0, what's this voltage here? Think back 15 minutes ago or 20 minutes ago when we talked about this, right? That voltage has to be what? This is 0, it has to be a VT plus VDSAT, right? That's the voltage on this gate, right? What happens when I reduce this voltage by amount of VDSAT? What will happen to this transistor? We'll turn it off, right? So if this goes down by a VDSAT, this goes up by a VDSAT, what's going to happen? This one will turn on harder. So here's a good question for you, okay? So if I have voltage across this now will be VT plus 2 VDSAT, where VDSAT 0 is the original DC bias VDSAT, right? All right. How much current will be going through this side? How much will it increase? If I increase the VDSAT, I increase the voltage on this applied to VT plus 2 VDSAT, how much current, more current will be going through this transistor? 4 times? Right, exactly, right. So this is the overdrive, right? So basically we increase this, we'll have 4 times more current coming out, because that's that square root thing, right? Okay, good. All right, so let's now look at a plot of V output. So what's going to happen is one transistor, as we increase VID, and this, at some point in time, we're going to begin to cut off this transistor and turn on this one, okay? As this transistor turns on, that means more current is flowing through here, 4 times if we just do it by VDSAT, right? That means we'll have more voltage drop across this resistor, so this node goes negative, right? So the output will become more negative. And we can keep doing that, right, until this transistor is completely off. And if that transistor is completely off, what happens then is that all of this current has to be going through this side. So we then know what this voltage has to be. Right? What's it going to be? It's going to be equal to minus, it's going to be at VDD, when this guy's all the way off and this one's on really hard, it's going to be VDD minus ISS times RD. So think about what happens. So a small change in voltage on the order of VD sat begins to have big changes on this output, because this guy's being to turn off and this guy's turned on hard, quadratically. Then what happens is all of this guy gets totally turned off, this guy gets turned on, all this current thing goes through here, and this will go to the most negative that it can. What happens to this side? Where does it go? This transistor's off, VDD. So this guy goes up to VDD. Okay, so this guy, so we can now have a, yeah.
Before the imbalance, you have ISS over 2 flowing through both branches, right?
Yes, right, exactly.
And then you drop the right gate by VD sat.
Right.
And then you get 4 times as much current in the left.
Well, I guess the point is it goes up sort of quadratically. I guess it won't be exactly. There's 2 currents. If this guy's not really turning all the way off, right? You know, his current the VD sats aren't a fixed value, right? So they're beginning to change on us, right? So that was a little bit. The point I was trying to make really is, what on the order of what size of change of voltage does this big transition occur? And it's on the order of the initial VD sat, but it's not exactly because the VD sat's different. Okay. So here's the plot you end up getting. So this is kind of on the order of the initial VD sat 0. Okay. So it's like a few tenths of volt. This thing makes a transition. Now remember, the output, differential output is, so this side V output 1 was equal to VDD minus ISS times RD. This is the maximum it can go to, right? The other side, V output 2, goes to VDD. So V out differential is V out 1 minus V out 2. What do we get? This is going to be equal to minus ISS times RD. The VDDs cancel out. Okay. So this thing will do, it'll go down and flatten out at minus ISS RD. And it'll happen very quickly, in a few tenths of volts. Okay. Similarly, flip it around, have this go up, this go down, it goes the other polarity, right? So this is the output slope. And this all happens in a few VD sats, okay? And so, now this is the large signal analysis. Typically what we're going to do is work with very small signal voltages, right? And typically our input will be a VOD to the small signal one now. So where does that fit in this curve? When we talk about small signal, what I'm really talking about was what's happening right around where VOD is very small, which is right around 0. So I'm looking at that slope right in the center here. That's the small signal. So that's the connection between large signal and small signal. But this circuit, you can see, goes into, you see large signal effects pretty quickly, right? Because this doesn't have to change for more few tenths of volts, and all of a sudden, bang, you're into this saturation situation, right? Gain goes to 0 at that point. I mean, here you have, slope of this is your gain. As soon as this thing saturates, you have no gain. You know, input changes, no change in output, right? You know, this delta input, you get a nice, good little change in output here, but out here you get none. Okay. That's the small signal stuff. What happens with large signal, or with a common mode? We should maybe talk about that for a second. It's a little, I hate to redraw this. It takes me too long, but I guess I can do it. Okay, so okay, so here, let's talk about large signal for a second. Here's V out 2, V out 1, V out 2, V in 1, V in 2. Now let's talk about common mode. What does common mode mean? It means the average value of these two. So here's how you can do common mode. You take these two leads, tie them together, and make it V input common. Okay? So the average value of these two, if I tie them together, is the common mode voltage. So if these voltages change together, then these two outputs will change together as well, right? Everything's symmetrical. Okay? Now, here's a little, that's very nice. Okay. What happens, here's, let's say I increase V input common. So that means I increase the voltage on the gate on both sides here. If I increase the voltage on the gate, generally don't we think that increases the current? Okay, let's say that's true. So we increase the current through these two things, and sure enough, if current increases, we'll see a change in resistance across this, and we'll see these two output voltages drop. But there's something wrong here. If these two currents increase, they sum together to a current source. Current source can't change current. So what's going to happen? See the problem here? In other words, if I increase these two voltages, and if current increases, but the current right here is the sum of the current. This is IDS1, and this is IDS2. ISS is equal to IDS1 plus IDS2. In fact, we said that the current's going to split equally because this is a symmetrical circuit. So typically IDS1 will be equal to ISS over 2, which equals IDS2. That all seems to say that these currents are fixed, but I just changed the voltage. How can they be fixed? Use your microphone. Use mic.
You increase the voltage across the current source.
I increase the voltage across the current source. Can I do that?
If you increase the current.
So if I increase this current, so if I take these two voltages up, can I just increase that voltage right there? Why not?
To keep the same current, you keep the same current, so you increase the voltage at the source of the two transistors.
Right. Yeah. He's absolutely right. That's exactly what happens. This voltage here has to move. It has to move to track. These currents can't change because it's fixed by this ISS down here. Any voltage is fine across ISS. It's a current source, right? So that doesn't hold the voltage at all. It only holds the current. So when I lift these two voltages together, what's going to happen is that source is going to track right with it. It's going to keep this voltage right here equal to what? VT plus VD sat. It's not going to change. So for common mode voltage, what would happen, this thing just goes up and down, and these currents don't change. So what is the output common mode voltage? What happens to it? It remains 0, right? There's no new, the common mode gain. A change of common mode input to common mode output is 0. There's no common mode change of voltage. Okay. So that's kind of how this thing works, right? Differential input, it saturates very quickly, but we have gain, common mode. This circuit, if we had an ideal current source down here, we would have no gain. All right, so common mode and differential seem to, the gain idea is very important. So that's what's interesting about this. So we'll define a new two-port, differential two-port, okay? The differential two-port will have common mode values and differential mode values. So this is I have two inputs here, but I'm going to define these new variables. After I define these variables, I'm going to define some gains. The gains I will define are, where are they defined? I don't see them. Okay, so let's define them right here. So V output, let's call it A differential mode gain, ADM, differential mode, okay? This means if I put a purely differential signal in, this is the gain I see, and that's basically defined as output differential over input differential. This is small signal ideas now. This is all small signal. So these gains are small signal gains. We don't define gain for large signal. That's just DC parameters, right? Just like our common mode gain is equal to V output common divided by V input common. So then you can see V output 1 equals V output common, so V output differential over 2. If I want to calculate the voltage on this node right here, I can use this formula. I can replace V output common by this formula right here. So it's A common mode times V in. Well, actually I took one bigger step here. If I put in, this is this differential in, differential out. I only put the input on one side and grounded the other side. So what is the common mode, what is the differential mode input for this? It's this minus this. So Vn differential is Vn minus 0, which is equal to Vn. The common mode value of the input is Vn plus 0 divided by 2. So the common mode input, the average value of the input, is Vn over 2. So so this circuit where I have an input on one side and 0 on the other side of a differential circuit like this, right, has both common mode and differential mode parts. I can then use these formulas right here, differential mode gain, to figure out what the output differential value is. That's what I did here. I want to find out what the output differential value is, so I substitute A differential mode times Vn gives me the output differential value, right? Divided by 2, because I'm just solving for this. I guess here, I'm working with this formula right here. I'm trying to calculate this value here. So take V output differential. It's equal to A differential mode times V input differential, and A differential mode times, and V input differential we said here is equal to Vn. V output common is equal to A common mode gain times V input common, which is equal to A common mode gain and times Vn over 2. V output 1 is V output common or V output differential over 2. So V output common is A common mode times Vn over 2. There it is right there. This is missing a 2 here, I guess. Right. Missing a 2 right there. And the output common is A differential mode times Vn over 2, right? Because of the 2 right here from this. So that's how you get common mode and differential. Now, what's important here? Notice I did not get a V output differential as a function of the common mode input. So I mean I didn't a differential common mode term. We assume this is 0. We assume there's no creation of differential mode signals from a common mode input, or we assume there's no common mode creation from a differential mode input. So you put a pure differential mode signal in, you get a pure differential mode signal out. You put a common mode signal in, you get a pure common mode signal out. And that comes from this symmetry. That will be true if this thing is purely symmetrical like I'm talking about. There's no cross terms that will ever be generated. If that symmetry is broken, then you can end up with some common mode creation or differential mode creation. That's typically very, very small. Even though transistors aren't exactly the same and all kind of stuff, that's generally not a problem. So we generally just assume, here's how we'll do these problems. We'll calculate everything as if it's differential mode, and get a differential mode gain, put that to the side, go do the common mode problem, purely common mode, get the common mode gain, and then we use these little formulas like I just did right here to calculate values of each one of these two inputs if we need to find that. Or if we just need to calculate the ratio of common mode, the differential common mode output and the common mode input, well, you just use this formula right here, the one I just showed you right there. Okay, so we'll finish this up next time, and then we'll have in the first half lecture, and I'll have to leave then after that.